Hi, everybody. Welcome to our first ever Tech Talk. This is Liz Fisher, and I'm glad that you all have joined us today. As you can see from your screen, which I hope you all can, we have an airflow monitoring station, a control sequencing blessing, a commissioning, and O&M curse. Our Tech Talks are starting this month. We will go through the rest of this year, except for the month of October, when I hope to see you all at NCBC. These Tech Talks are something that started in our central chapter as a way for them all to meet in their geographically challenged chapter, and they would take turns presenting these 30 to 40-minute presentations that were very granular, very technical as a way to get information out. What we hope to do over the course of this year and then next year, we want to have other chapters join in and present and give Tech Talks, so each chapter will take a turn. These are a member-only benefit. We are recording these. We are working with our current host for our website to get a place to put the recorded webinars in a format that you guys can see, but still have it be a member-only benefit. So we're working on that, so you will be able to go back and see these. However, probably the first one and maybe the second one will be a little bit delayed as we get that going. So bear with us as we get it set up for the recordings, but we didn't want to delay with our technology in getting these out and going. So the central chapter I want to thank for helping us get this year set up. We've already had other chapters step up for next year and have some great ideas for next year's. If you are interested in presenting maybe in one of these Tech Talks or have an idea you would like to submit, please send it over to Sherry or I, and we'll make sure everyone knows, and we can get it out to the chapters. We did send out a survey, and we have some of those already to go. So thank you again, everyone, for attending. I hope you appreciate and enjoy this. John Villani is, again, like I said, with the central chapter. He's helped set them up there. He is currently a director on our international board of directors and has presented many times for us. He's a commissioning provider engineer with Grumman Backus. And with that, I'm going to turn it over to him and let him take over from here. Thanks, John.
Great. Thanks, Liz. Thanks, everyone. So this presentation is created by myself, some friends, some manufacturers that worked with me. So hold on to your seats. We got a lot of material to get through, and I'll give it my best shot. If you have questions, send them in the little chat window, and I'm hoping Liz and Sherry will see that and can chime in. And sitting with me is Kevin Vanderclay, one of my coworkers and BCA board member in the central chapter. So you may hear him chime in. What we're going to cover today is a little refresher on airflow and doing traverses. We're going to talk about some of the technology, not all of it. What I realized when I spent many hours this weekend putting this together is I bit off more than I could chew. So there may be some things we don't cover here. I apologize, but I'll give it a best shot. Then we're going to talk about design, construction phase, commissioning items, things to look for, with lots of real-world examples woven throughout that. And some sequences of operations. And just like everyone's house, when it comes to airflow monitoring stations, it's all about location, location, location. So, refresher. Airflow is extremely dynamic. Okay, you're going to have varying velocity profiles depending on where you are in the system, which is my comment about locations and where you're trying to measure that. Multiple sensing points are going to be critical. We'll discuss that. And as always, the more measurements you take, the more samples you take, the more accuracy you're going to have. So a little quick refresher. So let's talk about actually just traversing. Let's talk about sensing locations. There's kind of three standard methodologies for that: log linear, distribution measurements, and you can see an example of that. A lot of this is going to come from the AMCA, or the Air Movement and Control Association. I've got that up here. And let me just pause 1 second. Sidebar is there's a ton of information here. I'm not going to read it all. I don't expect you to write it all down. this will be available after the fact. So I have more words here or pictures here. You will be able to go back and look at this as a refresher. So with that, I have a cover of the AMCA manual where it talks about some of these measurements if you want to know more and read more about that. This is an example for what they do for circular ducts. This is the log linear. Notice the circles and the holes are not equal distribution. Then we have the log Tishbachev distribution. That's going to put a higher sampling rate along the perimeter, okay, to get sort of that surface friction effect of what's going along the perimeter. That is one of the distribution methodologies to be looked at. You'll actually see that. I'll show you an example of that in a second. And then you have what I'm going to say is probably more common, is the equal air distribution. So these are three different methodologies used for traversing. However, if you look on the right, you'll see the Ebtron, one of their publications talks about sensor distribution in yellow, and they do equal area, or the log Tishbachev, or however you exactly pronounce that. I will say you see air monitor in the bottom right corner. Some of these slides are from one of their presentations they've given in our office, and they supported me in putting this together. So you'll see different manufacturers popping up here and there, and that's my way of providing them some recognition of some of the source material. So three different methodologies for distribution, whether that's doing a traverse yourself or whether that's actually going to be for your air flow monitoring station. The equal air distribution you're seeing here is going to be one of the more common methods you'll see out in the industry of how they do it. Notice it's not as many sensing locations as some of the others. So that's kind of a point of question. I'm not going to say I'm the expert of designing these. I'm just kind of giving you examples of differences between them. Now, where is that relevant? Why is that relevant? You're going to see a couple slides here. These are 3D profiles. What you're looking at is the velocity profile, okay, with the air going through a duct. So the airflow is sort of going up. And this was like the traverse point. So here's a point, here's a point, here's a point, here's a point going through, and then going back. So each one of these little boxes in your 3D graphic would be a traverse, and you see different velocities. And the point is, this is the same duct, same location. The profile you see on the left and the profile you see on the right are not the same, and that's just a function of how much air was going through there at the time, but it changes the profile. So the velocities are different based on the amount of air going through there, and you're going to see different sensings needed to pick up those variations. This becomes really relevant when you talk about putting a flow station downstream, upstream of something like an elbow or a change or an obstruction, a damper, etc. So these are just a couple examples to give you guys to show you the velocity profiles differences. So the top left is 12 duct diameters downstream of an elbow, which basically means it's turned out and come back to laminar flow. It's almost a flat velocity profile. The top right is when you're only 4 duct diameters, and you can see the top of the profile up here is higher than the yellow, which is lower down over here. So you're seeing that it's not a smooth velocity profile. And as we go to only half the duct diameter, the bottom graph, you can see a very significant difference in the velocity profiles. The point of these velocity profiles is to say that these are going to get harder to measure when you're closer to things like an elbow. And where are we usually measuring? Close to an elbow. Using some CFD modeling, this gives you an idea of how things actually look when they do the CFD model. So top left is a half a duct diameter from the elbow, middle is 1 duct diameter, and to the right is 2.5 duct diameters downstream. And as you would expect, going from left to right, you have an airflow angularity or angularity difference greater than 90%. You can actually see some eddy current effect going backwards here, and then you have a very large diversity. we're going to talk about that. That's hard for an airflow monitoring station to handle that amount of angularity in the flow station. It's just not meant to handle that. Okay, as we go 1 duct diameter, you can see things are starting to smooth out, but you still got 52 degrees of angularity in there. And as we go 2.5 duct diameters down, we're down to 20%. Now that 20% is going to come back in a part of our conversation later. That's a very manageable amount of angularity. These others exceed what we can typically handle. Just 2 other examples. This would be a sweep elbow. So this is a 1/2 duct diameter. Even though it's 1/2 duct diameter, we're still within 31%. And if we're degrees, I'm sorry, yes, I said percent, yes. And if you're 1 duct diameter, you're down to 26 degrees. So just kind of giving some refreshers here of what's happening with the air, understanding that the air actually, because of its mass, is going to be having a significant impact as it goes around an obstruction or an elbow. Okay, so there's my traverses refresher on air and the dynamics of air. Now we're going to get into some of the technology. Going to hit a few different types. The first being thermal dispersion. I will say our office does quite a bit of these. Ebtron being one of the manufacturers that's out there that's common. And they use thermal dispersion, okay, with glass bead thermistors. Okay, these are super high calibrated NIST traceable glass bead thermistors, and they are heating up one of them to measure temperature. They're heating the other one up, and actually in one of these holes, these black holes you'll see another picture of this later. There's 2 glass bead thermistors. One's temperature. The other one, they're heating up, and they're measuring how much heat is dissipated off of that to actually perform their calculation of airflow going through each of the holes. So there's 4 holes on this tube. You might have a couple of these tubes in your duct, and they're then going to average each one sensor individually, okay, so they can come up with their CFM. Ebtron's one manufacturer that's using thermal dispersion. Air Monitor is another. Similar, although different technology. They're not using a glass bead thermistor. They're using a thermistor that's on a little printed circuit board. Okay, but you can kind of see same thing. One thermistor measures the airflow. The other is externally heated to get the differential of the airflow to the dispersion temperature. And that's how they do it. So both of them use a very similar kind of algorithm. These are fairly robust. They work very well. We've had good success with these this type of technology.
Hey, John?
Yes.
Do you want to take questions as we go?
Sure.
So we have a question that says, our firm specifies turning vanes in all 90-degree elbows. Is that not done some or most of the time?
I would say that is done most of the time, especially on supply ducts. I did not have CFD modeling for ones with vanes. That will significantly improve that air angularity. So the question goes back to one of these. I would basically say a sweep elbow, and I don't know this, I'm going to say emphatically, but the difference between one of these square elbows without a turning vane and a sweep elbow, I think the impact or the effectiveness is the turning vanes are going to give you more of a result like this. You can refer to each manufacturer, and they will have guidelines to tell you if you have an elbow and you have turning vanes, kind of what their recommended distance from that elbow. There's still an impact with the turning vanes, just like a sweep elbow, but it's definitely going to be better than one of these.
But you also might get maybe a 45-degree kick or a 30-degree kick or offset transition, and that would kind of give you that same effect of an unvaned elbow. And that's a type of fitting that you would not get turning vanes in. So something else to consider as you're looking at placements for these.
So jumping back to technology, so yeah, jump in, Liz, if there's questions that come in. So pitot tube, this goes back quite a while ago. I did a little history lesson here this weekend. Henry Pitot, who was a French scientist, was trying to figure out how to figure out the speed of ships back in the 1700s. About the same time Bernoulli was coming up with his equations. And basically what you have today is basically what he figured out in the 1700s was this whole concept of the relationship of total pressure and static pressure and being able to come up with velocity pressure. And once you start to know that and the area, you can start to do some calculations to figure out things like CFM, feet per minute, speed, etc. So that's the principle behind it. What you're looking at there is a couple examples. Most of us have seen a balancer, we have a short ridge, whatever it may be, and we can do our pitot traverse of a duct to go through that. And what I want to refresh here, not everyone maybe understands it, is when you have your pitot tube, basically you're measuring total pressure coming in the front port, and you're measuring static pressure on the side port. You can kind of see that again in the yellow and the white. The white is your total pressure, the yellow is your static pressure, okay? You cannot measure velocity pressure, which is what we really need to figure out. But you take the difference of those two, velocity pressure being total pressure minus static pressure, to come up with that, okay? What I have here is an air monitor picture of one of their setups. Again, and I'm not promoting these manufacturers. I'm just saying these are ones that we work with a lot. There's other manufacturers, so I'm not trying to be negligent of other people out there. Just these are a few that we worked with and had pictures readily available. So that's the pitot tube. Now let's dig into that a little deeper. I will not go through this whole calculation, but what I wanted to do is provide it so you guys can see what's going on here. Is you need to figure out your velocity pressure. So I'm going to go back 1 second, sorry. So again, velocity pressure is total pressure minus static pressure. If you take that velocity, okay, which is going to be your velocity pressure, take the square root of it, multiply it by 4005 as your conversion factor, you can come up with your feet per minute. And that's your flow velocity in feet per minute. Then you need to add into that your area. So in this example, 1.77 square feet. Do the math, and you come up with, in this example, 6,000 and change CFM. So little homework lesson of how that's all being done. Now, one of the most important things, I should have put my little tech tip symbol here, okay? Tech tip symbol, you'll see that later, is in this example, the velocity pressure is 0.75 inches, okay? That is the difference between these two, 0.75 inches. One of the problems we have absolutely seen is fan walls, high static pieces of air handler, where the pressure transducer measuring those are not sensitive enough. They'll come in with a 0 to 10 pressure transducer, and we're trying to measure 0.75. So when you take your accuracy of that transducer and you say it's across the full scale, and then you realize you're measuring way down at 0.75, you start realizing there's a ton of error in that, way more than you realized. So this is an area of caution, tech tip. Be careful of the pressure transducer that they're using when they're doing these. This would go for the piezo rings as well, where you have pressure transducers. So just a note here, pressure transducers are a source of error if you don't have the right one. You want one that's appropriate for the range of what you're going to read. Pitot tubes, one of the things the Air Monitor did, and there's a few others out there, is they enhanced this back in the, Fetchmer was back in 1922. I found some information on him when he was putting a patent together for centrifugal fans. So this guy was quite brilliant. He figured out that, hey, instead of just having a port on the front and a port on the back, I can do a better job of handling what we call the airflow angularity, and that's what you're seeing down here is what they call pitch and yaw of the air. That's the air moving over the pitot tube to handle more air instead of it coming straight on, having some movement there. So the pitot-Fetchmer method basically is more of a design where you put a static pressure sensor port on either side a certain number of degrees apart. And that's what the current basis of air monitors design is around that. They can handle more angularity. So in red on the left, it says basically angularity of plus or minus 30 degrees. So they're saying they can compensate for something like this diagram in the middle with 52 degrees of angularity. That may be pushing it. It also helps with shorter lengths of run. So just giving you an idea that not every pitot tube out on the market is the same. There are some differences. Inlet bell technology, whole nother can of worms. You're seeing air monitors on the top left. You're seeing Paragons in the top right. You got Ebtrons with their setup in the bottom. Bunch of different technology. I guess I will say on my soapbox, because I'm giving this, not a huge fan of inlet bell. It's a source of very high velocity. There's been some articles talking about things like when you bolt these clamps on the inlet bell, it has an impact to the airflow. It's the highest velocity in the whole system, so there's a system efficiency impact. These are very common, highly used, but on the other hand, they're also at a very dangerous point in the system, i.e. right on the inlet of the fan, and we'll come back to that. So my little note here, remember this picture, copper versus poly. We'll talk about that later. These are very common though, and we'll see other examples as I get into the good, the bad, the ugly pictures later.
And I'll also bring up that as far as the sacrificial loss to the pressure that the fan can handle by installing these probes, the Paragon is quite a bit better because there's not as much really in the high velocity portion as the air monitor. However, it's very critical where they actually install the tubes coming in. You can see this one, they've kept it off the inside of the ring and down, and you can even see them be brought straight down and then right into that way. So it's at the lowest velocity point of the fan inlet. We've had issues in the past where they ran the tubing right along the bell housing and then down, and that caused all kinds of pressure drops.
Piezo ring, you guys may have heard about it, seen this. This is becoming more popular. It's sort of a neat, clean way instead of the inlet bell. And this is where you're going to have a high side pressure, which is sort of this port right here. It's kind of on the face of the bell. And then right before it goes in the fan, you're going to have this ring here of ports. And you'll see all these little holes going around that goes into that. And that's going to be your low side pressure. So what they're doing there is they're using the pressure differential and then the shape of that inlet bell. They've done the calculations to figure out what that is, so they can take the difference in pressure and the area to come up with CFM. Again, pressure transducers are deployed, making sure that they're the right size range for what you're measuring. I would say the most common error we see in commissioning is the transducer is too high of a range, too big of a range, and we're measuring something much smaller. So, you know, 0.75, you could use a 0 to 2 inch range pressure transducer, and they show up with a 0 to 5, 0 to 10, or something like that. So, little information about this. These are a little interesting. We've seen a bunch of these where it comes from the manufacturer, but it seems like the paint shop paints over the inlet bell ones on the inside, what we're going to call the low pressure ports. They're along here, which is right on the inlet. We've seen those kind of get painted over, so like, yeah, I'm not sure they're going to work. The other piece is these are common with fan walls, or at least our experience is they're common with fan walls. And the problem with that is, depending on the sequence, not every fan is running. So you start getting weird measurements, and what often happens is, if you can imagine, there's, let's say, a 6-fan array. You've got 6 of these. They put them all together. So all the high ports come together, all the low ports come together, and it's one big massive averaging. And suddenly things start to get really sideways on you. So especially if not all the fans are running at the same time, at the same speed. So
yeah, one thing to look for in the review is that they each have their own individual
pressure transducer,
right, to avoid that.
Yeah, now, to Kevin's point, he just said if you have a fan array, you got to go through and make sure each one has its own pressure transducer. That is, if there's a theme to this whole presentation, is it's way down in the weeds, it's way down in the details. There's so many little pieces to be paying attention to for airflow monitoring stations. And that's a great example of, yep, the drawings show it, yep, it's in the fans coming with the P0 ring, great, yep, the controls contractor diagram shows it's got an airflow station there. I've checked all the boxes. Looking to see that he's actually got 6 pressure transducers for the 6 P0 rings, you've got to be way back in that control submittal to figure that one out. But that's what it kind of takes to make sure these things are coming together properly.
Or even if they're using Ebtron inlet sensors or something like that. A lot of times we've seen in the past where they specify 2 sensors at 2 of the 6 fans or 12 fans or something like that, and then they're planning to average it out. Everything we know from air profiles is not every fan does not do the same amount of airflow. So really, to get accuracy, you need to measure at every fan.
Yes, concur. Just a little example here, and this is not pushing one technology over the other, rather than to just highlight that they're not the same, and they each have their pros and cons and benefits. Thermal dispersion versus pitot tubes have different performance curves. So, at lower velocities, the thermal dispersion, okay, velocity is along the x-axis here. At lower velocities, the thermal dispersion is going to be able to give you a much better signal output and kind of sense what's going on, but then it kind of flatlines up at the top at the high end. The pitot tube is sort of the other way, okay? It likes to see high velocities. It wants to see some good velocities, okay? It's not going to perform as well at the low end. So just to highlight that there's some differences here. Okay, that is the section on technology, and now we start getting into sort of some of the commissioning things. And each of these stories are real jobs, real examples, real world. I like to learn the hard way. That's how I learn best, so that's what these fall in that category. This is an air handler, one of our projects. We were called in to do some troubleshooting a couple times. This is the return section of the fan on the right. You're coming through the recirc damper here. The exhaust damper is on the right side. And then up here on the top, you have the minimum and maximum OA dampers. The airflow station, number 25, was the minimum outside air airflow station. I will say that this is a hospital project where minimum airflow is sort of a thing they really pay attention to. You just see that 25 note here. The design called for only the minimum OA to be measured. The problem with that was any time we went in economizer, which is a larger damper, the min OA fell below in what's measured. It fell below the minimum required. So the owner kept saying, how come we keep going below our minimum OA? Well, that's because we're in economizer mode. I can tell you intuitively, it's obvious you're bringing in more than your minimum OA, but I can't give it to you definitively. In applications like that, when places like Joint Commission comes through, they want to see trends, they want to see histories. This is sort of an OPR-ish, we didn't meet what the owner needed. Really, the solution would have been to measure the whole OA. Would have solved a lot of that issue. But let's continue with this story. Here is the sequence of operations, and that is the return damper and relief damper shall modulate in opposition to maintain the minimum scheduled outside air CFM. Now, this wasn't so much of an issue in econ mode, but understand what they were doing is if you're not getting your minimum OA, they're going to close the recirc and they're going to relieve more air. They're going to try to pull more air, suck more air through that minimum OA damper. And this is conversations not economizer. This is just regular operation mode. So what you see highlighted is for just regular running. Is if you're falling short, you're going to start to close off on that recirc damper or return damper. This is what you're actually looking at. These are pictures from the field. Top left is the outside air coming from left to right, dropping into the unit. This bottom left picture is looking from inside the unit, looking up. You have a minimum OA damper on the right, a maximum OA damper on the left. Notice the airflow station is not down here in the air handler. It's actually up above that minimum damper in the top right picture with a couple Ebtron stations running across. They built a little baffle plate. This is, again, another picture on top of the air handler. Here's your access door right here, and that OA station is over here, okay, to give you some perspective of where things are. Here's a field report I had to write when I got called that they kept, on yellow, continued tripping problems of air handler 2 on low suction static safety. Air handler 2 is experiencing safety trips as a result of the measured minimum OA being below set point, which per the sequence had the return air being closed, forcing the air handler to draw more outside air in. Going to the point where the return air was going completely closed, trying to pull something like 20,000 CFM through a very small OA duct. The low static safety was properly set to 3 inches. And what we found when we went through this 24 by 24 access door, we crawled to the right about 5 feet. What you see is what it looks like when you look at an OA airflow station. This could be any manufacturer. I'm not picking on anyone's, but it looks filthy and dirty. And that is not going to do thermal dispersion very well when you have a big hairball sitting on there. This is an operational issue, an operational problem. It would have been much nicer had they, do I have it in there? No. If they had put the OA station somewhere right near this access door and measured the whole thing. So if you're doing commissioning, this story talks about design review issues, it talks about O&M issues, etc. Field installation, how are you going to maintain that? Really, they should have put another access door right over here on the side so you could get in there on each side of the OA duct so you could get in there and maintain it. It's not fun to crawl through here to get down over there. This is another project, design phase. We got involved in airflow coming from the bottom, going up the page, turning left to go through a return airflow station. Remember the pictures of the CFD models. That's not going to make for a nice laminar flow going through this airflow station. Interestingly enough, there was an exhaust one here, and this exhaust one was right up near a damper, which was causing all sorts of weird back pressure and weird readings. And all of these dampers were starting to, or airflow stations rather, were starting to play into each other and what was happening and how the sequence worked for fan tracking. So that brings in a question. This was a location of no turning vanes because it's an exhaust relief or exhaust return fan here. There's no turning vanes for this airflow station. That is going to make some interesting challenges of what's going on there.
John, do thermal dispersion sensors know which way the airflow is moving?
I don't think so.
No, they don't.
Yeah, they don't. They don't.
Any eddies or currents or anything like that will read as airflow,
Yep.
but it will will kind of get lost, that some of it might actually be going the wrong way, and yet it's counted towards the total.
Right. So Kevin's point is what happens right over here when you get a weird eddy current, thermal dispersion doesn't show up that these sensor ports are a negative. They just see that they're dissipating heat. So it gives you a false positive reading. Good comment. Here was an interesting point, was just to say Air Monitor has what they call their flow straighteners. That might be a solution to try to help. It is from a technology standpoint, but in the bottom picture you see what happens when it's unfiltered on the return side.
The prefab beehive.
Yeah, it looks like the beehive. When you look in a duct and see a beehive, that's what it is. Here's one of the more complicated ones I've worked on. This was the design drawing. Notice the red bubble is sort of the inlet and relief area. This project had a heat pipe. So we had maximum OA, minimum OA, and relief air. Relief's going over the heat pipe and covering, trying to basically provide the heat pipe, the source of heat for the minute OA. That turned into, yep, that's just a blow up of the same thing, which we're just looking at. That changed somewhere along the way to construction to this drawing, which has maximum OA on the bottom, minimum OA over the heat pipe, a certain amount of relief over the heat pipe here, and then sort of your economizer relief up here. This was a project that we were looking at for some seasonal testing and troubleshooting. It's winter time here in Chicago at 28 degrees. This is what I call a 5 airflow station headache. You count them up, 1, 2, 3, 4, and another one over here, 5. There's a lot of flow stations. The flow station company was very happy. Made a good profit on this job. But what was going on was something wasn't working. We were picking up way too much heat through the heat pipe, which was great, but what was going on was we were way short on our min OA. What we found was that the max OA airflow station was kind of all out of whack. It was not reading properly. So if you are an Ebtron fan, you'll see this once or twice in this presentation. Here's my tech tip for you. Remember this, if you see a lowercase m under feet per minute or CFM, if it's a lowercase m, that means you have a bad sensor, or one of your probes has a bad sensor, and you can figure that out. So this example basically had a bad max OA airflow station, caused a reduction in the minimum OA over the heat pipe. Then we had another issue of an improper sequence maintaining the exhaust air over the heat pipe. That was a different problem. And we had too much air going out through the econ relief up here. So what I have in the bottom was a field report where we basically wrote, we'd like to propose a new sequence in economizer mode, okay, and we talked about how that was going to be done. And not to get super technical because it gets into the numbers for the project and the heat pipe and airflows, etc. But it brings up the question, should the CXP be making recommendations like this, where if we find a sequence is not actually taking things into account? And as you recall from the design drawings, there was only one relief. The field construction ended up with 2. The sequence never got changed, so the controls contractor never changed it. So my point is, I think the answer is yes, you should be making these recommendations. You should be running them up to the design engineer and the controls contractor to problem solve. Because by the time you are this deep into a problem like this, you probably understand it better than anybody else. So I will say the philosophy I will tell you in this tech talk is that yes, we recommend, or we suggest that you should be making recommendations like this of sequences back to the engineer. So here's my Ebtron tech tip. Look for that lowercase m or in CFM or feet per minute. That will be your indicator. It's right here on the screen. That's your indicator that you've got at least one bad glass bead thermistor.
Will it rule it out of the equation if if it is bad?
Nope, it does not. It stays in effect. So actually, great question. What happened here was this was not reading. I literally was able to go and we were able to disconnect the actual whole probe that was that had the bad sensor and only rely on one. Now granted, that's less sensing ports, but it actually gave us a more accurate reading doing that because the bad sensor was throwing things so far out of whack that it was causing the extreme problems. It actually was leading to things like freeze-stat trips. So this was you need to come up with something to solve the problem to keep the unit running. Airflow sequences with airflow stations. Obviously, the blessing and the curse here is we've got this great technology, and now we can use the real data. The curse is getting them maintained and really incorporating everything in the sequence. The next two slides talk about building pressurization a minute, and one of the common things that's done is to link the relief damper, the recirc damper, and the max econ damper or max OA damper. A lot of times these are sort of inverse control signals. And we start doing things like min OA measurement, we do return fan measurement, we do supply fan measurement, we do some fan tracking. And I'm not going to go through all the numbers here, but what I'm advocating if you're doing commissioning is look at all these numbers, see what makes sense. And in this example, when I go through the numbers, what I realized when they talk about return damper CFM, okay, return fan CFM, what I realized was they didn't leave any air in the building for building pressurization. There was nothing in there to account for that. And the numbers on the top right are where I started playing around with, well, what should these numbers look like? What should they be? Now, one of the comments here is, in this example, we are not in economizer, so the econ damper would be closed. However, because I've got some building pressurization, I need to relieve a little bit of air. So I need to exhaust a little bit of air. I need about 1800 CFM, which means this would have to be cracked open just a little bit to exhaust, but this damper would be closed. So when I say don't link the dampers, it's because you can actually find yourself where you need them to be not at the same positions. If I take all of this and we talk about building pressurization, and I would say in today's day and age, we're seeing a lot more sequences with building pressurization. You'll notice I have it talking about 10% for building pressurization. This is my little discussion on that. We find often building pressurizations in the 10 to 15% range, and that is percent of supply airflow. We typically are having fan tracking calculations taking that into allowance. So what that looks like is return fan CFM is equal to supply fan CFM minus fixed or measured exhaust CFM. Now, what do I mean by fixed or exhaust? I mean like toilet exhaust, general exhaust, something like janitors' closets, bathrooms, etc., minus building pressurization offset. So if we put some numbers to that, it's about 1800 supply. We've got 910 for toilet in general. We got 10% of 18310 is 1831. So if you do the math, this comes up with your set point. So don't forget when you're looking at these airflow station sequences, don't forget some building pressurization. If you don't see that in your sequence, that's a design review comment. Question that. What's the fixed exhaust? You've got to go through the floor plans and look at what that is. A lot of times the controls contractors have no clue what the fixed exhaust is. So this is where, again, commissioning can help figure out and fill out some of these numbers.
John?
At 1:45, I'm getting very close to the end. Do we have another minute, Liz?
Yeah, I have one question for you. Have the speakers found that monitoring the MA plenum pressure a way to better manage these damper arrangements?
I'm going to say it's a very slippery slope. That is a really hard measurement point. The mixed air plenum, you're measuring really, really low pressures of slightly negative, slightly positive. It becomes cumbersome to try to correlate that. So I'm going to say the answer is no. I've not found that to be a reliable, sustainable, easy means to fix that issue. Have I seen it? Yes. Have we struggled with it? Yes. But I won't say that it's kind of like a, oh, great, here's an easier solution.
It might be a good monitoring point, though, too, because to see what the pressure is there obviously tells you what, how your air handler's running. And if the pressure goes screwy really without anything else apparently changing, it's probably a good indication that it's time to check your sensors and your airflow measuring stations, things like that, because something's not working right anymore. So I would agree that it's maybe not the best thing to use as an active control, but it is a informative monitoring point.
Yeah, that's a great point. So just picking on all of the technology together, there is no one technology that's the foolproof, bulletproof, best sliced bread thing out there. I'm just highlighting lots of differences. The plugged honeycomb beehive, the dirty thermal dispersion sensors, inlet bells. You can see why they're really not my favorite, because if I want to get in there to clean them, I've got to take this whole cowling cover off, grill off just to get in there. And they're, again, high velocity, things are going to stick to them. I've seen over greased bearings and then grease sprays all over these things. So it's a tough O&M spot to get to, kind of a pain. You've got to have the fan down for a longer period of time. This is an example of, notice a little poly running in here, a little poly tubing. We'll come back to that. Here's Kevin's example he was talking about before. This is the Paragon example. This is a real job. The picture's on the top left and top right. Real job. The before and after. The after, this is that actual same job with all the copper in there. How do you get a contractor convinced that they need to do this is a great question. Well, it's really easy when they suck the poly tubing into the fan and shred the whole fan and have a catastrophic failure. Then they finally take that commissioning issue that you put down, it wasn't installed per manufacturer's instructions, a little more seriously. That is a true story on these fans, which were about 25,000 CFM each, I think. That was not a cheap catastrophic failure times 16 of these. Yeah, luckily they only failed one of the fans. So point of information here is pay close attention to this.
And I think they installed them between site visits, like, within a periodic site visit every 2 weeks or so. They all installed them between those, so we couldn't even tell them to pump their brakes and change course. So something if you're feeling nice and generous to bring up as one of the things you're going to be looking for if you're seeing these on your projects.
Yeah. Lesson learned is look for this. Talk about this early when they're talking about rigging these. These are installed in the field by a controls tech or a contractor, etc. So they are literally Sharpie marks. You can see a little bit of the mount down here. They're penciling. They're trying to figure out how to mount these things. It's not an easy thing to mount. Thanks to my buddy over at Canon who had this great example of a pitot tube array, very large air handlers. This is a project in Chicago, a library that they were working on. They were sharing information with me. The O&M staff admitted they had never cleaned these things, and they were in active control with the sequence of operations for fan tracking, so never maintained.
How do you clean these, John?
Well, look in the IOM. It'll talk about it. In general, there's kind of the two parts. One, on the pitot tubes, you can literally just wipe down the gold tubes going up and down vertically here. Get those nice and clean. So that's going to be just your rag, etc. However, the airlines, if you disconnect the pressure transducer, a little compressed air blowing it backwards goes a long way to kind of blow out a lot of the gunk in there. And that's been recommended by a bunch of the different manufacturers. Here's a real installation of a thermal dispersion. It looked great on paper until it showed up in the field, and we had this big structural support in the air handler, and we have one for the min OA damper, and we have one flow station. Down here, we had some really weird distribution of why they put them where they did. It was just a really ugly. Now, here's the interesting part of this. If you were to turn 90 degrees from this whole damper section, there was a long straight run of OA ductwork. Okay, that would have been perfect. It could have measured all the OA beautifully. I mean, it was like a 30-foot long section of OA ductwork. Recommend you talk about this in the field. When they're citing these, honestly, most of the controls contractors just know they have them, they carry a budget, and then you work with the manufacturer to talk about it. So if possible, get engaged with that conversation about where they could use these, where they can mount these things that are accessible, give you good readings.
And a lot of the manufacturers, our reps have dealt with this enough and the headaches involved that they are often proactive and volunteer to get out there and help locate them in the field when it's time to install them. So
yep.
Lean on them as much as possible.
So again, sorry I'm running over. Just at the very end, tab and calibration. This is coming from Ebtron's book. Here's a tech tip. Nowadays, a lot of what all of us are facing is static pressure reset, which means we're running our systems up for max cool, max heating, and we're running them way down for unoccupied modes, okay? Which means we are at two ends of a spectrum. If you have a 25,000 CFM air handler, you know, you might be running normally at 22, 23,000, and unoccupied, you're down at like 8. Okay, which means that airflow station needs to get calibrated to handle two very far ends of the spectrum for the minimum and maximum. We are putting in our commissioning program, you know, when we do design review, when we do comments, when we talk about the tab and the balancers, we're saying, hey guys, you need to do the 2-point field adjustment, okay, the 2-point calibration for max and min. Look for something like this in whatever project you have. Most of the manufacturers have something better than the 1-point you see at the top. They have a 2-point. And I'll say that has been a big game changer when we start to work with these static pressure reset programs. Kevin, here's your field report. One of the problems, now we're seeing a lot of big air handlers, 50,000 CFM and up. What was the story? Since you gave it to me?
Thanks. Put me on the spot here.
This is
okay. Thank you very much. Sorry. All Ebtrons are calibrated for velocity, and then they take that signal and they convert it to an output of typically a 0 to 10 volt output, and you can adjust that the scale of it. So even though it can handle, you know, 4,000, 5,000 feet per minute, that might translate to a much higher CFM than you really need it to do. So when you purchase them, you're kind of saying, all right, this is going to see typically no greater than 30,000 CFM. They might say, all right, then we'll set your top of scale at 35,000 CFM. That way, your 0 to 10 volt output signal corresponds to a 0 to 35,000 CFM range. However, if things change, or maybe this was lower use now, increased use in the future, and now the future is now, and you need a higher output scale, it's an easy thing to correct. However, you got to look at it at both things. Both the Ebtron transmitter itself needs to be adjusted, and then the BAS where you're actually taking that signal needs to be adjusted as well. Any savvy controls contractor will know how to do it. They just might not they get a little bit leery that they could be screwing up the calibration, and this does nothing to change that calibration. It's still a factory calibrated probe. You're just helping or changing the scale of that output. So obviously, we don't want to say it goes up to 50,000 CFM if it's only going to see 25,000 CFM. We want that scale and the sensitivity of the or the accuracy of that output signal to be as good as possible, but it is something that's easy to change.
And what I put in bold from the field report is need to change the scale on the transmitter and the scale on the BAS so the signals match. Lastly, we've got some cleaning instructions for Ebtrons. Ebtron had something earlier on I meant to highlight. It said Ebtrons don't need to be cleaned. Footnote 1. And then you come all the way back in the manual and find footnote 1. It says, if no pre-filtering is provided, you may need to periodically clean and inspect the filters using compressed air or a small brush. So thus my pictures from my story of climbing 5 feet down the duct to find these dirty OAs. Yes, they all get dirty. You need to know how to clean them. So how do you clean a flow station such as an Ebtron? Well, okay, first you should override your dampers so they don't go all haywire when you start trying to clean them, okay, so they maintain whatever position they're in. And at least with Ebtrons, you need to turn the transmitter off. You don't start blowing compressed air and brushing them and things of that nature with the thing fired up. So here's a little diagram of how to do that. This was something we had put together, okay, and again, look for the lowercase m for CFM or feet per minute. Basically, find some type of instructions, O&Ms, and include that in your systems manual. Operations and maintenance will need to clean these things and know how. Here is the actual published document from Ebtron. So include that in your systems manual. The question is, when do I clean them? And my common answer is after it stops snowing in the spring, which around here is the cottonwood tree season. So we have what looks like snow flying all over the place, usually about April, maybe late March, April, and early May. When that's all done, I say go in there and clean those darn things. That's kind of my usual. If you're doing it only once a year, that would be my my recommended time. But you know, twice a year, I like to have them do it. If they're doing filter changes, hey, that's the time to look at it.
Right, and I would also say if you're in an area that's freezing, you'll have the pollens and cottonwoods in the spring, so it'll affect your summer. But in the winter, if they're still dirty, when they dirty up, they don't read. They read less than the actual. So if you don't clean them before the winter, you're likely to start bringing in more than anticipated OA, and you might start having pre-stat trips. So I would recommend the fall as well.
There you go. And lastly, when you're doing filter changes, have them take a look at these things. Put this in your systems manual. Say, look at this as part of training. This should be part of the routine maintenance. Inspect these things. Here's one that's actually broken off. Again, if it was actually bouncing kind of around, vibrating. At some point, that thing was going to get sucked into the fan inlet and cause, again, catastrophic failure. So, you know, something to look at. With that, I thank everyone. Liz, any questions? And I put my companies down there where I've gathered information, my sources down there. So thanks to all of those folks for helping put this together. Liz, questions?
Nope, you've answered all the questions that we've got. We have more than gone over time. So I am going to close by thanking everyone for attending today. And we look forward to seeing you in September for our next Tech Talk. And look for an email from Sherry. You will get all of the information at that time. Thanks, everyone. Bye-bye.